4.4, number 162. We are told to use the mean value theorem for derivatives and find all points .0 less than c less than 2. Right? So find all points c in this interval such that I'm going to write it down here, f of 2 minus f of 0 equals f prime c times 2 minus 0. Which is the same as saying, if I divide both sides by 2 minus 0, f prime of c equals the average rate of change of the function f on the interval 0 to 2, right? The way we had it written before when we introduced the mean value theorem. This is just the book's way of writing this same expression. Just divide off by 2 minus 0 to the other side and isolate f prime of c when thinking about it. So the function they give us is sine pi x. So although it's not integral to this problem to draw this picture, I want to do it just to explain what's going on in the problem. X and f of x here, which is our sine pi x. So the period of sine pi x is the old period, right up here maybe. Period is the original period of sine function, which is 2 pi, and divide off by the coefficient on x, which is pi, and I get 2. So therefore, I need to see from 0 to 2, it turns out I'll have a single period of the sine function. So if we call this, let's do it by halves here, half, 1, 3 halves, 2. So from the origin until this location, we should move through one period of the sine pi x function. So it will oscillate between -1 and 1, as we know. So starting at the 0 value here, we should have a peak, a 0, a trough, and then another 0. And then this pattern just continues forever. But we're not really worried about anything outside of the 0 to 2 interval. I'm just going to draw this just to indicate it does keep going on forever, of course. All right, so there's our picture. So let's see what we have here. F prime of c. F prime of c is, of course, the derivative of this function. And for some location we don't know yet, but it's got to be in the interval 0 to 2. All right. Now over here we have the average rate of change of this function on the interval 0 to 2. So that would imply, right, here's 0 f of 0, and here's 2 f of 2, and then we draw the secant between them. It's overlapping the x-axis. And the slope of the secant in my picture is exactly this average rate of change here, and it looks like that's 0. From the appearance, it looks like 0 in this case. So let's calculate it just to make sure using the formula. So f of 2 would be, write it like this, f of 2 minus f of 0 over 2 minus 0, even though my picture is pretty convincing, but just in case, the whole thing's to be done analytically anyway. We'll have sine pi 2, so sine of 2 pi, minus sine of pi 0, sine of 0 pi, or 2 minus 0. The sine of 2 pi is 0. Sorry, sine of 2 pi is 0, that's this location, and sine of 0 pi is this location. So we get 0 minus 0 equals 0 over 2 is, of course, 0. So we were correct, right? The blue secant line slope is 0. All right, so now this is supposedly equal to the derivative of this function, which I guess is clear using a chain rule here. We would have cos, right, the outer function differentiated, inner function left the same, times the derivative of inner function. The derivative of pi x is just pi, of course. Right? So that derivative should be equal to the slope of this secant. Well, looking at the picture, I'm looking for tangent lines which would be parallel to this blue line. Probably this peak here, we have a tangent line with slope 0, just like the secant. And also down here at this trough, we should have a tangent line of slope 0, just like the secant. So it looks like in the interval 0 to 2, there are two places, looks like 1/2 and 3/2, I guess, right? I guess for C is 1/2 or 3/2. So it looks like there's two places in this particular context where the tangent line slope would be equal to the secant line slope.